All right, so today we're going to continue with this last functional group from this chapter, epoxides. All right, so epoxides are actually just ethers, but they're a specific ether that's kinked into this three-membered ring here. Right, so this is our simplest epoxide that we can have here. All right, we can have other carbons coming off. They can be longer than that, but they're all going to share that same structural feature of that three-membered ring with the oxygen. These epoxides, they're much more reactive than all the other ethers. Right, so although technically an ether itself, we're going to put it in its own little functional group category and talk specifically about reactions of epoxides, what do we think is going to make them so much more reactive? The little triangle that they're in. All right, so this little triangle is much less stable because of what's called ring strain. I'm sorry, angle strain. Right. Our carbons are these sp3 hybridized carbons. So they want to have a bond angle of 109.5 degrees. All right, that tetrahedral bond angle. All right, but in our three-membered ring, in our triangle, that bond angle is instead what? If we have this equilateral triangle here, what are our angles going to be? 60 degrees, yes. For an equilateral triangle, we have these three equal bond angles of 60 degrees. Quite a dramatic difference between that ideal bond angle and our actual bond angle. So that's going to explain why these epoxides are so much more reactive than other ethers. Okay? In particular, epoxides, we're going to see a common theme in our reaction of epoxides. They're going to undergo what we call ring opening reactions. All right, so they're all going to have this same basic reaction here. Right, so we're going to have some nucleophile that's going to react with our epoxide, and we're going to see this ring is going to open up here. All right, so we're going to break this carbon-oxygen bond in these reactions. So first of all, we're always going to get this alcohol functional group in our product. We get this hydroxyl group. All right, to be clear, that hydroxyl oxygen, that was my oxygen in my epoxide. All right, another sort of signature of these epoxide reactions here. Let's note we got two carbons in our ring. We're going to color one of them red and one of them blue. All right, the signature of these ring opening reactions is we have our nucleophile attached to one of those carbons, and the hydroxyl group is on the other one, right? So we're always going to see this same 1-2 carbon spacing between our hydroxyl group and our nucleophile that we've added. All right, 1-2 carbon spacing in our OH and our nucleophile that we've added on there. Cool, and so we've talked about nucleophiles in our previous chapter. We kind of made this little bit of a cheat sheet of our nucleophiles that we're going to see a lot of. All right, we're going to sort of talk about these same set of nucleophiles. We have our strong nucleophiles. These are easy to spy because they have those net negative charges for the most part. There was this weird sulfur one that can be neutral, as well as our Grignard, which is a little weird because we have that carbon-magnesium covalent bond, right? We don't usually see metals, but because of that, we have this very polar bond in our Grignard. And then our weaker nucleophiles are those neutral forms of our oxygen and nitrogen nucleophiles, all right? So we're going to talk a lot about that same group of nucleophiles, but we're also going to talk a lot about our conditions for these reactions, all right? And we're going to break these nucleophiles up based on our reaction conditions. So the first one we're going to talk about, all right, so let's label these our epoxide mechanisms. All right, and the first one is basic conditions. Okay, it is super common in organic chemistry to catalyze reactions by changing the pH. So we'll see a lot of reactions that are catalyzed by acidic conditions. Other reactions are catalyzed by basic conditions. In the case of epoxides, we'll actually see that they're reactive under both, all right? So we need to kind of keep it straight by what we mean by basic conditions and acidic conditions. So by basic conditions, we very simply mean we cannot have any strong acids, right? A strong acid is not going to survive under basic conditions. All right, let's take a look at a few strong acids here and see if we can't figure out what structural feature they seem to have in common. All right, so an alcohol is not a strong acid, but if we protonate it, that is a strong acid. Likewise, the classic strong acid is the hydronium ion. All right, what we're going to see is a lot of our strong acids, they have a hydrogen on an atom with this positive charge here. All right, so when we're drawing these mechanisms and we want to make sure to avoid strong acids, we're going to kind of boil this down to a simple rule here. No positive charges. All right, we don't want to see any positive charges on our intermediates. That's how we know we're going to be avoiding any sort of a strong acid. All right, now that's not to say that we don't need to do proton transfer steps. All right, so proton transfer steps, we're going to still need an acid, something to play the role of a proton donor. We just can't use a strong acid. So instead, we're going to use a weak acid, a very weak acid, like water. Okay, so we're going to see we're going to need to do proton transfer steps. All right, we're going to need something to be a proton donor. Under basic conditions, we're going to use water. If we need a base, if we need something to be a proton acceptor, well, under basic conditions, we can use that strong base hydroxide, right? So if we do need something to accept a proton, we can use that strong base. We just can't have any strong acids, so our acid in our mechanisms will just be water. Okay? We can also say, not going to be super common in these ones, but in other reactions, an alcohol can also play the role of a proton donor, right? It just can't be a strong acid. All right, so let's look at our list of nucleophiles here. Let's see which one of these, I'm just going to copy this over, are electron-rich species in our reactions. All right, we're not talking about alcohols anymore, so I'm going to get rid of this business. What we want to do is look at our nucleophiles here and see which ones are going to be compatible under basic conditions. Okay, so all of our strong negatively charged nucleophiles, these are all going to be compatible under basic conditions. Everything that has that net negative charge, that's an easy way to spy a basic conditions nucleophile. The only kind of oddball up there that doesn't have a charge but is still considered a basic nucleophile is that Grignard reagent. Grignards are also strong bases. They are not compatible with acidic conditions. Right, so basic conditions, these are our negatively charged nucleophiles. We'll say plus that Grignard. Cool, so let's grab one of these here. We'll do our alkoxide ion. And let's do our mechanism with our epoxide. All right, so here's our epoxide. We're going to have these deprotonated ethanol or ethoxide ion. All right, and we're going to do our mechanism keeping in mind our conditions here. We should only see negatively charged intermediates or neutral intermediates. We don't want to see any positive charges here. Okay, so hopefully you've gathered what's going to be playing the role of our nucleophile, given that we were just looking at the list of nucleophiles here, right? So my glowing red hot, tons of electron density here. My alkoxide ion is my nucleophile. All right, and it's going to attack, where's my electrophile here? It's going to be my carbon in my epoxide. All right, so first of all, why is this carbon going to be our electrophile in this reaction here? Well, it's in this polar bond with oxygen, right? Oxygen's much better at pulling electron density than carbon is. So we indeed have this polar bond, all right? But most importantly, the thing that really makes that oxygen or that carbon a good electrophile isn't just that it's in this polar bond. We see carbons in polar bonds with oxygens all the time, and they're not playing the role of an electrophile. So what makes it a good electrophile is it's got this built-in leaving group here, right? My nucleophile can attack that electrophilic carbon and kick off that pair of electrons in that ring opening reaction, right? Because that carbon's just so ready to get rid of that angle strain, this pair of electrons right here is going to be very easy to break. That bond is going to be very easy to break and donate that pair of electrons to that oxygen, right? So we got this built-in leaving group pair of electrons here, which is also what makes that carbon such a good electrophile, right? What makes these epoxides so much more reactive than normal ethers. So everybody take a second and draw me my intermediate here. All right, since my ether oxygen has accepted this pair of electrons that was in that carbon-oxygen bond, now it's not got 2 but 3 lone pairs. And since it's got 3 lone pairs, what am I going to make sure to include?
Negative charge.
That negative charge. All right, so given our product here, right, we said that our epoxide oxygen is going to become a hydroxyl group. So what's this last step in my mechanism going to be? Given what we discussed about basic conditions, I want to see if everybody can finish off our mechanism. We need to protonate that oxygen. All right, so we're going to need to use one of our proton donors. In this case, I wouldn't mind whichever one you used. I will say that if we're going to use an alkoxide ion, you usually use them mixed with their protonated version with an alcohol. So typically in our reaction mixture, we would have this ethoxide and ethanol mixed together. And so that's what we want to do here. All right, we're going to use that alcohol as our proton donor. Notice that that will replenish the supply of alkoxide ions in my solution as this reaction occurs. Right, I've reformed my nucleophile by reacting with that solvent. All right, so we have our ring opening reaction, our nucleophile attacks, and importantly, because we're under basic conditions, we don't have any positively charged intermediates here. All right, so now let's look under acidic conditions. Right, under acidic conditions, how do we know that our mechanism is correct? We should have no strong bases. All right, so what we want to do is avoid our negatively charged intermediates. now we're going to say no negative charges. All right, there are a few notable exceptions to this. The real rule is no strong bases here, right? The no negative charges is just kind of a helpful little thing to keep in mind as we're drawing our intermediates to make sure that we didn't make any mistakes, all right? There's some notable exceptions here of negatively charged things that are not strong bases, and those are our halide ions, right? So we're just going to say except chlorides, bromides, iodides. Even though those have negative charges associated with them, they are terrible bases. All right, and like before, we're going to need to do some proton transfer steps. So again, we're going to want to use an acid or a proton donor. All right, now we're allowed to have strong acids under acidic conditions, so we can use that strong acid, that hydronium ion. All right, but importantly, if we need a base under acidic conditions, if we need a proton acceptor, we can't use a strong base like hydroxide. We're going to need to use a neutral base like water. Okay. If we want to look at our list of nucleophiles and try to think what's going to be compatible under acidic conditions, right? We can't have any of our negatively charged nucleophiles under acidic conditions. They'll just immediately be protonated by that solvent, by that environment. So we're going to have to use our neutral nucleophiles under acidic conditions. All right, so under basic conditions, we said we could use the negatively charged ones or our Grignard. For acidic conditions, we're going to note we want to use our neutral nucleophiles. Now, for all but one of those, that weird sulfur, sulfur is just such a great nucleophile, our thiols, our other neutral nucleophiles are these weak nucleophiles here. We're going to see when we take a look at our reaction mechanism that that's okay. Under acidic conditions, these epoxides will react with these weaker nucleophiles. So we can get away with using an alcohol or water or an amine, something like that. All right, so let's take our epoxide and we're going to react it with one of our neutral nucleophiles here under acidic conditions. All right, let's use that good nucleophile, that thiol. So let's just try the same thing we did last time, all right? In our previous mechanism, that first step was nucleophilic attack. Let's do that this time, all right? We're just going to kind of try something out here. Boom, boom. All right, so then if I draw my intermediate here, my sulfur has attacked, so now it has this positive charge. It's only got one lone pair. And my oxygen has now accepted that lone pair, has this negative charge. All right, is this an acceptable intermediate here under acidic conditions? What's wrong? That negative charge, right? And that negative charge, again, is just a sign that we have a strong base. And indeed, this alkoxide ion is a strong base. This thing will never form under acidic conditions. So this can't be our first step in our mechanism. What you're going to see is that we're going to have to use these proton transfer steps. These are going to be used to help manage our charges. Right? So if you do a step in your mechanism and you're like, oh crap, I'm not allowed to do that. That creates a strong base. The answer is go back and do a proton transfer step first. All right? So this isn't going to be our first step. Instead, we're going to protonate that oxygen. All right? And since we need a proton donor, we're going to use that hydronium ion under acidic conditions. All right, but that first step is going to be to protonate that epoxide oxygen. All right, and what we're going to see is this is going to help us manage our charges here, avoiding any negatively charged intermediates. Now, if that oxygen accepts that extra hydrogen, it's going to have a positive charge associated with it. Okay. Now we can do our nucleophilic attack with our thiol. All right. And if we look at this intermediate here, this positively charged epoxide, this protonated epoxide, the reason why we're able to get away, and in this case we have our strong nucleophile, but even if we had our weak nucleophile, the protonating of that oxygen weakens this bond quite a bit. Now that oxygen is even more willing to accept that pair of electrons. Right, so by protonating our epoxide, we make it an even better electrophile, which is why we can get away with our weaker nucleophiles under acidic conditions. All right, given our product here, I want everybody to take a second. There's going to be 2 more steps. See if you can't fill in for our epoxide mechanism under acidic conditions. At the end, again, we're going to have our nucleophile attached to 1 carbon. And our hydroxyl group located 1 carbon away. All right, so after that nucleophilic attack, our sulfur is still got that proton on there. So our last step is just going to be another proton transfer step. All right, just to name these, the first step was a proton transfer. Then we had nucleophilic attack. Now we're going to need 1 more proton transfer step. All right, but this time it will be to deprotonate that sulfur, meaning I need a base. What base are we going to be using under our acidic conditions? Yeah, water. Some neutral molecule. We can't be using our strong bases. So yeah, let's go ahead and use water to deprotonate that sulfur. And we've just regenerated that hydronium ion in the process. Cool. So epoxides, their reactions with nucleophiles are catalyzed either under acidic conditions or basic conditions. When we're looking at our mechanisms, we want to make sure that under basic conditions, we don't have any positively charged intermediates, no strong acids allowed. And under acidic conditions, it's the exact opposite. We shouldn't have any strong bases. So we're looking to avoid any negatively charged intermediates. All right, so thus far we've been looking at the very simplest epoxides. All right, let's look at some more complicated epoxides, and we're specifically going to be talking about the regioselectivity of these reactions. All right, again, we're going to sort of divvy this up based on our two conditions. So basic conditions, we're going to see one rule for regioselectivity. Acidic conditions, we're going to see another rule. All right, I'm going to just leave some space up here at the top for these two. There's going to be a pretty simple rule that we're going to fill in, but let's see if we can't reason what that is here, looking at some more complicated epoxides. All right, so now instead of using just my very simplest epoxide, now I'm going to use one that's a little bit longer. So instead of 3 carbons, we got a bunch more on here. All right, we're going to react this thing with our cyanide ion. And given this nucleophile here, what conditions must this reaction be under, acidic or basic? Basic, right? This is one of our basic nucleophiles. So for right now, we're going to be looking at our basic condition reactions. All right. Previously, my epoxide was perfectly symmetric, so it didn't matter which side I attacked on my nucleophile, I would have gotten the same product. All right, I'm going to color these 2 carbons in my epoxide, orange and green, so we can keep track of who's who here. All right, and now let's ask ourselves, do we think our nucleophile is going to want to attack that green carbon? Or is our nucleophile going to want to attack our orange carbon? Why orange? Steric hindrance, right? It's more accessible. That nucleophile needs to be able to get to that electrophile. Which one is more accessible? It's going to be that orange carbon there. All right, so yes, we're going to say not this one. Our nucleophile attacks the more accessible carbon. All right, so our product, everybody take a second just for practice. Draw me the product of this reaction then. We don't have to do the full mechanism here. We're going to skip that last protonation step, but just give me the product of our reaction here under basic conditions. so I'm going to start by drawing those two carbons. Okay? And we're going to talk a little bit more about this next class, our stereochemistry of these reactions. But you're going to note I'm always going to kind of draw about that epoxide bond where my new bond is pointed in the opposite direction of where that hydroxyl group is. In this particular example, it wouldn't have really mattered, but we're going to see a lot of examples next class period where it does. So getting yourself into this habit is going to be really good. All right? As we said, we should have that cyano group attached to that orange carbon. I'm going to be good and draw it linear about my triple bond because that's my geometry. And that means my hydroxyl group is going to be on the other carbon, my green carbon, the one that didn't get attacked. All right, and again, notice that I have this little zigzag pattern going on of my nucleophile and my hydroxyl group. Again, we're going to see why that's important, so I would just get in the habit of drawing that like that now. Now, I'm not quite done. I still need to include those carbons that were already attached to that green carbon, so that's what I'm going to do down here. My 1, 2, 3 carbons, and we're already on my epoxide. Cool, all right, then just for fun / practice here, everybody take a second. Draw me my products of reacting an epoxide with a 3-carbon Grignard. Right, again, we're going to have that accessibility argument. My nucleophilic site here is that carbon that's attached to that magnesium. So I colored that kind of dark blue here. So I'm going to add just those 3 carbons onto my more accessible epoxide carbon. And then we have our hydroxyl group on the other one, plus those 2 carbons that were already attached. Right, so as we said, we have that more accessible carbon being attacked. And so what we can kind of convince ourselves up in our examples here is that if we have a primary carbon, that's going to be the one that gets substituted. Our secondary carbon, if there's no primary, and then last on that list would be any tertiary carbons, right? So that's our regioselectivity under basic conditions. Okay, now you wouldn't think that the conditions would really change much, and to some extent, primary are still favored over secondary under acidic conditions because of that simple accessibility argument. But there's something weird about tertiary carbons in epoxides under acidic conditions. All right, and let's remember that's because our very first step in our mechanism is different for acidic conditions than for basic conditions. So let's now look at acidic conditions. All right, we're going to take an epoxide that has a tertiary carbon. Right, and remember now that very first step in our mechanism is that protonation step. All right, so if we have a protonated epoxide, all right, now remember we said that we can react these protonated epoxides with our weak nucleophiles. We can get away with our weak nucleophiles under acidic conditions because we've created an even better electrophile by protonating that oxygen. We've weakened that carbon-oxygen bond. But if we look here, there's going to be one carbon that's going to be much better at holding that positive charge from that weakened bond, and that's going to be our more substituted carbon. So the way that they kind of illustrate this is by showing that this bond over here has already started to break a little bit. All right, they draw this dotted line here. And this represents this bond has already started to break. All right, and so how can it get away with starting to break that bond? Well, when that bond breaks, that pair of electrons is going to go onto that oxygen, meaning that the carbon has to hold some positive charge. And what do we know about tertiary carbons and their stability of holding carbocations? They're the most stable of all of our substituted, right? So these tertiary carbons are going to be more willing to hold that positive charge. Thus, the bond's specifically going to break on that one side. This carbon over here doesn't want to hold any positive charge. It's primary carbon. So that bond's not going to start to break. All right, so when we do our regioselectivity of our epoxides under acidic conditions, it's actually going to be any tertiary carbon is going to be the most likely to be substituted. And then we get to our regular sterics argument. All right, so we have different regioselectivity for these epoxide reactions under basic conditions than under acidic conditions. Under basic conditions, it's a very straightforward accessibility argument. Under acidic conditions, for specifically those tertiary carbons, you get this weird metastable state here where that bond has already started to break. All right, so then for the sake of completion here, let's take our tertiary epoxide, react it with one of our acidic condition nucleophiles, and everybody's going to take a second and draw me the product of that reaction. right, so now our nucleophile is going to attack that tertiary carbon because the bond on that side has already started to break. So that's where my nitrogen's going to be added, and my epoxide oxygen will have formed a hydroxyl group on the other side. All right, now notice, as we've said before, whenever we use our neutral nucleophiles, they're going to need to lose a proton in order to be attached on there. That last step when we drew our mechanism. So even though my nucleophile is NH3, my product is NH2. It's lost a hydrogen in that process. Cool? All right, so what we're talking about, and we're going to sort of pick this up next time as well, is our epoxide reactions. Epoxides are these triangles. They're super pissed off because they don't want to have a bond angle of 60 degrees. They want a bond angle of 109.5. So they're going to undergo these ring opening reactions, and they can do so under these two different conditions. Basic conditions where we shouldn't see any strong acids, or acidic conditions where we shouldn't see any strong bases, and we have different regioselectivity depending on our conditions. Cool. Next class we'll talk about stereochemistry, everybody's favorite.